This is Dr. J. Mohan. I am going to discuss about the signals and stochastic processing in the topic of uniform distribution and exponential distribution. This topic is going to map with CO of 4, that is extended the random variable concept to random process, and it is sample functions for demonstrating the time domain and frequency domain characteristics. This CO4 is mapped with PO4, that will be represented as range of conflicting requirement. That range of conflicting requirement consists of completely addressed complex engineering problem. It's involved with the uncertainty, ambiguity, and impressive information and wide range or completing technique in the engineering field. And sustainability goal, it's mapped with this topic as quality education, affordable and clean energy, climate action. This is the outline of today's discussion. The uniform distribution, we should study about characteristics and discuss about the property of uniform distribution. For the exponential distribution, we go for the properties, cumulative distribution function, common application, as well as some example. First, we go for the uniform distribution. The uniform distribution is represented as uniformly distributed for the certain range of interval in the property condition. So, I represent for the uniform distribution is a continuous probability distribution where all possible outcomes within a given range have the same probability of occurring. The probability density function is represented as 1 by b minus of a for all value of x in between the minimum as well as the maximum. I should represent for the uniform distribution in the probability condition in graphical way. The continuous probability I represent as a x. So actually we write for the probability, we studied for the last class, the probability P of capital X equal to small letter of x. So this is we call for the probability density function. This probability density function, this x we consider as a continuously going to happen in the probability. That value, I take for this value as a x-axis of small letter x. Then probability density function, that f of x, we write for the f of x. This f of x I take for here in the y direction. So in between the interval of minimum value a I take, the maximum value I may take to b. So in the a and b, the probability is represented as a uniform. So the probability is going to occur in the uniform cases. Okay, this what is represented as a uniform distribution. The key concept of uniform distribution is continuous as well as of uniformity in the probability density function. The continuous is represented as a any value within a specific range of interval. So here we take for the minimum as well as of this is a maximum. So minimum is equal to small letter of a, maximum equal to small letter of b. So in between it will be going to happen, that is the probabilities of the equal value. That's what I represent as a continuous value. Next is a uniform. Every outcome within the range has a equal probability of occurrence. So see here, the probabilities are equal values. So this too is represented as a key concept of uniform distribution. Here we have for the taking two parameters in the uniform cases. The equal probability is going to occur in between the two interval. One is represented as a minimum, another one is represented as a maximum. The minimum we represent as A. in the graphical cases. Maximum is represented as a B. So that's what the uniform, it will be uniform is going to happen in between the minimum as well as the maximum value in the range. Next, we go for the probability density function. The probability density function is equal to f of x. I write as a p of capital letter x equal to small letter of x. This value is equal to probability density function. This is equal to f of x. This f of x will be happen as per the probability density condition. We write for the probability of events. How many events is going to happen for this graphical? This is a 1 events. Yeah. So the probability events is going to happen the 1. At the same time, the interval between the A and B, these two will be going to happen for the occurrence. So that's what I write as a f of x equal to probability of even is equal to 1. Only one possibilities are going to occur. At the same time, in between the two interval, what is it? In the maximum interval minus of minimum interval. That the maximum value is equal to B, minimum value equal to A. That's why I write as a B minus of A. So the formula for probability density function f of x equal to 1 by B minus of A. So this, what's the condition for the probability density function? The probability density function condition is going to happen in between the A and B, minimum as well as maximum cases. That's what I should write for the A lesser than or equal to x less than or equal to B. A is represented as a minimum value and B is represented as a maximum value. X is continuous distribution. The probability is going to occur in between the A and B. That is also we have the uniform. So A less than of x less than of B. Then x is falls outside the range, the probability density is equal to 0. See this graphical cases. So this portion is 0, then this portion also 0. In between A less than of x less than of B, only the probability is going to occur. That is f of x. That value is equal to 1 by B minus of A. Okay. So that's what the probability density function. It's going to happen by the 1 by 1 B minus of A. At the same time, remaining portion, all the values are zeros. Okay. So we represent by the graphical representation the probability density function for rectangular with a basis of B minus of A and a height of 1 by B minus of A, such that the total area under the curve is equal to 1. Next, we go for the characteristics. It's have the 4 different type of characteristics. One is constant probability density function. Second one is defined by 2 parameters, that is A and B. We call for the minimum and maximum. Then the probability density function is it's going to happen for the rectangular shape. The probability density function total area is equal to 1. So this is the 4 characteristics. First characteristics is represented as constant probability density function. The feature is the probability of any outcome with the specific range is the same. So what the graphical we represent for the uniform distribution, the x and the f of x. So this is the probability density function is going to happen for the minimum value as well as the maximum value. This is a uniform. Okay, the probability is equal to uniform. The probability density function, this value is equal to 1 by B minus of A. That is represented as amplitude. Here, the constant probability density. So see here, the probability density function doesn't get to change. It's a constant that will be considered as constant probability density function. And second probability of characteristics is defined by 2 parameters. What are the parameters? A and B. Okay, 2 parameters are there. So the interval of the probability, continuous probability is going to occur in between the A and B. So A is represented as a lower boundary and B is represented as a upper boundary. Next, we go for the shape of the probability density function. What the shape is, you can see this shape of graphical case of uniform distribution. This shape is look like a rectangular shape. So that's what we represent for the rectangular shape characteristics of uniform distribution. In this case, and the height, the rectangular shape height, this height is equal to 1 by b minus of a, and width, this is a width, is represents a b minus of a, we write. Next, total area. This total area probability density function is equal to 1. Why? Because of it will be going to happen for any probability of any events, the total probability equal to 1. The rectangular shape total area is equal to 1. Okay, that's what I write as a total area under the probability density function curve, representing the sum of all possibilities always equal to 1. Then we go for the next property of uniform distribution. It's going to satisfy for the 7th property. First one is equally likely outcome. Second one is parameters. Third one is mean. Fourth one is variance. Fifth one is standard deviation. Sixth one is symmetry. Seventh one is maximum entropy. The first probability, all the value within the defined interval. The interval is the uniform distribution is A and B have the same probability of occurrence. So see the graph of uniform distribution. The interval of minimum as well as of maximum is B. The amplitude is equal to 1 by B minus of A. The probability density function I take for the f of x, the continuous is represented as x. The probability is going to happen, this is uniform. Okay. So the interval between A and B, okay, A and B, the probability is represented as the same. For if the interval is increased A to B, the probabilities are same. That's what I represent for the probabilities equally like outcome. Next is a parameter. It consists of two parameters. One is represented as a lower boundary parameter. Another one is represented as a upper boundary parameter. Lower boundary parameter I make to represent for the A, and the upper boundary parameter I like to represent as a B. The probability density functions are uniform. Next property, mean or expected value. The average of parameter in the case of uniform distribution is represented as a mean. That mean I represent for the mathematically expected value. The expected value symbol is E of capital letter X is equal to the interval between the two average. What is the interval between the two? The minimum as well as the maximum. A plus B divided by 2. The variance. A measure of spread of data, as here we call for the variance in the uniform distribution. The variance is equal to B minus A whole square divided by 12. And the standard deviation, the square root of variance we call for the standard deviation. So standard deviation stands for S D capital letter X, that is equal to root of variance. The root of variance is B minus A whole square divided by 12. If you take for the root of variance, that square is going to remove from the upper part, B minus A divided by root of 12. Next one is a symmetry. The distribution is a symmetry. Why? The meaning is has no skewness. The skewness value is equal to 0 because of there is no changes happen when you are going to take for the uniform distribution in the probability condition. So in the level of A and B, the minimum as well as the maximum level, it's uniform. That's why skewness is 0. Next one is maximum entropy. From the given range, the minimum as well as the maximum cases, the uniform distribution has largest uncertainty or maximum entropy. So the probability of uniform distribution is maximum entropy condition. Next we go for the cumulative distribution function of uniform distribution. The cumulative distribution function f of x equal to x minus of a divided by b minus of a. Why we are going to write? Because of our probability going to happen as x f of x. In the uniform case, this is a lower boundary, this is a upper boundary, is uniform. This portion only it's going to happen for the distribution. This line we consider as a one single line, straight line. The straight line formula is represented as f of x equal to x minus a divided by b minus of p. The condition, the formula also appear when a less than of x less than of b. We write the graphical representation of cumulative distribution, and this total probability is equal to in between the a and b of uniform distribution. Probability is equal to 1. Remaining portion is equal to 0. This two portion is equal to 0. That's what I write as here. Cumulative distribution graph is a non-decreasing function that start at 0 for x less than of a. This portion 0 start x less than of a. X less than of a, and its raise linearly, the area is equal to 1 up to x equal to b. That means a to b, and the remaining portion, okay, x greater than of b is equal to 0. Okay, this what will be represented as a graphical representation in the cumulative distribution. It's going to have further two type of uniform distribution. One is discrete uniform distribution, another one is a continuous uniform distribution. The discrete uniform distribution, it's applied to finite and countable outcome because of discrete values. Then each possible value of random variable has equal probability. For example, rolling a pair of die. Each one it's going to produce for the probability is equal to 1 by 6. Then continuous uniform distribution. This apply when outcome can take on any value within a continuous interval of a and b. All values within this range are equal likely, but since there are infinitely many values, we use probability density function as some discrete interval. Here I take some example, choosing the random number between 0 and 1. Okay, it will be uncountable. This for the continuous case. First we go discuss about the discrete uniform distribution in discrete values. The discrete uniform distribution is a probability distribution that describes likelihood outcome as each outcome in the infinity state is equal likely to characterized. So here this discrete uniform distribution, we to measure for the probability mass function. The probability mass function also we consider as a probability density cases. The probability mass function P of capital letter X is equal to x of I. This x of I will be n number of possibility of outcome is going to happen within the some interval. So that's what the probability density function or probability mass function is equal to 1 by of n. Why? Because of n possibilities are going to occur in the interval between the our cases of a and b, that is minimum as well as of maximum value. So that probability is equal to 1 by n. For example, rolling a pair of die or flipping pair of coin where each outcome has equal probability. Okay, it is going to have other two cases. One is estimation of maximum, another one is random permutation. So what's the estimation of maximum? The maximum possibilities of occur in the uniform cases. The uniform case, the equal values. Okay, so that's what we represent as a maximum observation in data set of large value of probability condition. That is called for the estimation of maximum. Next is random permutation. The random permutation is rearrangement of set of item or elements. So here we have for the lot of possibilities going to occur for the uniform interval. We should arrange for ascending order as well as a descending order. If we make to arrange, all will be going to have the equal probability. That is represented as a random permutation. This is going to have for the some property. So first one is each outcome in this sample space has equal probability of occurrence and the probability mass function over the range of possible outcome. The mean of the discrete uniform distribution is average of the maximum as well as of minimum value. The variance is of uniform distribution is n square minus 1 divided by 12 and n is a number of possibility of outcomes. It will be going to have further some application. First one is modeling the sensor where there is no preference or basis toward any particular outcome. And another one is a sampling without replacement. Then another example is generating the random number for simulation. Another example is creating random permutation for shifting decks of cards, design, experiment, and cryptographic application. Like that, we have a lot of applications are there in the discrete uniform distribution. Next one is continuous uniform distribution or rectangular distribution. We call for the rectangular distribution. So the rectangular distribution or probability distribution where probability density function is constant within a certain interval and remaining is equal to 0. This means that all outcomes within the interval are equal. Its example is generating the random number in between the 0 and 1. So here we represent by the within the interval, that is f of x and here is f x. So within the interval I take for the a and b, the probability is equal to uniform. Okay, remaining part is 0. This total area is equal to 1. So that's what I represent as a constant within a continuous interval and 0 value for remaining portion. The cumulative distribution function of continuous uniform distribution is equal to f of x equal to x minus of a divided by b minus of a. This one we studied for the characteristics. So where will be going to happen? The minimum as well as of maximum. That's what I write as here. Interval of a less than or equal to x less than or equal to b. So remaining portion all is represented as a probability density function 0. That's what the interval. The interval is x less than or a and x less than or b. Okay, this portion we represent as a 0. For value less than e, the probability is equal to 0. The value greater than b, the probability equal to 1. For value within the interval a and b, the probability increase linearly 0 to 1. Next, we go for the generation of functions. Generation of function provide a way to represent the sequence of number of power series. How they are going to provide for the sequence of power series? The standard uniform distribution cases. The standard uniform distribution case, it's going to happen in between the interval of 0 and 1. So why we take for the 0 1? So the interval of a and b, the probability is going to increase in between the 0 to 1. That's what the standard uniform distribution also is going to happen in between the 0 to 1. Next, we go for the properties of continuous uniform distribution. So this is going to have for the equal probability density function within the interval. That's why cumulative distribution function is increased linearly with the interval of the minimum as well as of maximum value. The mean of continuous uniform distribution is midpoint of interval and the variance of continuous uniform distribution is b minus a whole square divided by 12. Application of continuous uniform distribution. It's going to using for the engineering. Most of the engineering application we are using the continuous uniform distribution because of uncertainty in the various field of engineering as well as the finance as well as the physics. That place we are using for the continuous uniform distribution. Why? Because of we measure for the what will be happening in the average. Next, we use for the random number when we are doing for the simulation case as well as a doing for the gaming application. So there need random numbers. So it is used in the statistical equality control to model the uniform in manufacturing process also. So this is using for the cryptography technique in the network security. So, okay. So this is using for the so many ways to apply in the engineering field. Up to this much, I'm going to stop remaining. We will see for the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.